Okay, so let me just start with a few remarks on what we did last time, because Michael raised some question at the end about this statement here. Then for some H and A's that exactly one, etc. And at that time I thought that maybe I misstated it, but in fact, after looking at it, it is correct. For some H and H, you should read as there are H and H's, right? Good. Anyway, we should then I started this section, this discussion of the ODE y double is Vy with V semi-algebraic. I with two lemmas about oscillating germs, and then I ended up with stating this theorem. And that is in some sense the, so now I should really start the next, oh, I can actually continue with this, I see, I can simply continue here. I didn't realize that. I thought oh wait. Oh no, I can't continue. I seem to have to start a new page. Is that right? I can't continue with the old page.
Why not? Why not? I mean, you can continue because you're going to give the proof of the theorem, I guess, right?
I think you did not select the pen. You selected the eraser.
Oh, right. Ah, right. Oh, okay. You're right. Okay, good. Yes, proof. Yeah. So this will take a while. So H is a real closed Hardy field, and you have a C2 germ that generates some Hausdorff field extension, right? That's of course equivalent to saying that G minus any element of capital H does not oscillate. Yeah, G minus any element of H, it can never oscillate. That's what generating a Hausdorff field is equivalent to. But we also assume that the second derivative is then in the real closure of this Hausdorff field HG. Then the conclusion is that G generates a Hardy field over H. And now we are going to give the proof, which is a somewhat lengthy, but I have plenty of time today, so I'll get through it. So maybe I should say, enter lecture 8. That's, and this is simply this is the main goal today, to prove this. This is also the main result in that paper of Bojanitsan that I mentioned. Okay, so first we are introducing the following Hausdorff fields. H, G, G double, right, which is contained in the real closure of H, G. Right, since G double is in this real closure, if once you join it, it's still, of course, a Hausdorff field, yeah, which is also equal to, since G double is algebraic over HG, this is of course the same as HG. It's the ring generated by G double over HG. And it is, of course, everything is in C2 now. All the elements of H are C2, G, and let me see. Oh yeah, because this is HGR. Yeah, I mean the reason is that this is contained in C2, right? This is the real closure of something that is generated by C2 functions. So, right. So G2, in particular, the second derivative of G, you might think it's only continuous because G is C2, but it's actually C2. Okay. In particular, right. Now, now we apply 512. Apply 512 to G double. I'll go back to in the row of FG. Yeah, let's go to 512. That was this lemma. If you have a Hardy field and two C1 germs, such that the first one generates a Hauser field over H, and the next one is in the real closure of that, then for this capital K, which is our K now, if you take derivatives, you end up in K plus Kf prime. So if we apply that here, we get that taking derivatives of elements in K, you get in K plus Kg prime. Okay, now we introduce the following collection of germs. Namely, all the elements in this real closure such that the difference oscillates. The difference with G prime. Right. Now, so, okay, this is just a definition. You take all the, everything takes place in this real closure, right? Oh no, wait, I shouldn't say that. G prime might be somewhere outside of this real closure. We don't know that. Oh no, actually, no, you're right. Actually, G prime, wait a minute, now I'm a little confused. Okay, anyway, this is just a definition. Now, F is, what does it mean for F to be empty? Well, then this is equivalent to, so that means that G prime minus any element in this real closure does not oscillate, which means that G prime generates a Hardy field extension of over K. G prime generates a Hausdorff field. Over the real closure. Right. And in particular, this means that it generates, G prime generates a Hausdorff field over, well, we can H, G, G prime, G double. Only a Hausdorff field for the moment. Right. But if that's the case, if in fact G prime generates.
Sorry, it's now it's over HGG double. No.
What am I? G prime generates a Hausdorff field over H G G double. You're right. No, actually, no. I actually meant G generates a Hausdorff field, namely this one. It does generate this Hausdorff field. But you're right, it's a Hausdorff field over H, G, G double, but the Hausdorff field that it generates is this one. Does that make sense?
Yes, it's okay.
Right, okay, yeah. But if G prime generates a Hausdorff field H, G, G prime, G double, then in fact it is a Hardy field. Then this is even a then yeah, this is even a Hardy field. Since all the quantities indicated are C1, this is certainly a subset of C1, even a Hardy field. So we only have to check that the derivatives are in there again. In view of, well, what we already mentioned about K, namely that delta K is contained in K plus Kg prime, and which is contained in H G prime G double. Right, and then and of course the derivative. So K is what G and G double generate, and G prime, the derivative of G prime is also in here, namely it's G double. So okay, good. So we are done if we can show that F is empty, right? And we would be done. We are trying to show that G generates a Hardy field over H, and and we would be done. So enough to show that F is indeed empty. It's empty. And now we are proving this by contradiction. Suppose it's not empty. Suppose towards contradiction, this is my symbol for a contradiction, that F is not empty. So there are germs F in this real closure such that the difference F minus D prime oscillates. And now we simply take one that is of minimal degree, right? These elements of capital F are algebraic over Hg and therefore over K. And so we can take one of minimal degree, let over K, let F in F be of minimal degree and greater than to 1 over K. And then of course you have the minimum polynomial. Y polynomial of F over K. Yeah, that's so Py is y to the power n plus, and let's write it out, P1 y to the power n minus 1 plus Pn, where the Pi's are P1 are elements, are coefficients in K. Now, Okay, so F is in little f is in capital F, so it's F minus D prime oscillates. Now, by definition of F, little f being in capital F, and so F, that means that Ft equals G prime T for arbitrarily large T. Now Pf is 0. And so, and Pg, well, what is Pg prime? You can also plug in G prime for P. Well, it's still, it's certainly C1, since G prime is C1 and the coefficients of P are C1. So, so let me see. Well, Pf being 0, of course, means that 0, when you plug in T, this is always, for sufficiently large T, this is going to be 0, but it's also equal to Pg prime evaluated at T for arbitrarily large T, for arbitrarily large T. So that means that Pg prime must oscillate. So Pg prime oscillates. Well, the only other possibility would be that Pg prime is actually equal to 0. Yeah? Otherwise, so let's just show that. Otherwise, Pg prime equals 0. So then, but then, you have Pf is 0 and Pg prime is 0. And they are both continuous germs. And then by an earlier result, 133, so one of the earliest results, it means that they have to be, since also Ft equals G prime T for arbitrary large T, they have to be equal. Yeah? So F equals G prime for F is G prime as germs. By, yeah, this was an earlier result, proposition 133. Yeah, and this contradicts that F minus G oscillates, right? Contradicting, because the 0 function is not considered oscillating, contradicting F minus G oscillates. Okay, so that is okay, so let's underline what we have now. Pg prime oscillates. Good. Now it will be useful to call this set H is Pg prime. Some C1 germ for the moment, and it's an oscillating one. And let me see, where am I? Right. So, but if you have an oscillating germ, C1 germ, then its derivative must also oscillate. Yeah. So H oscillates. By the underlining. hence, yeah,
I mean, you said that f minus g prime oscillates, right? Can you not apply immediately the fact about the derivative and conclude that f prime minus g double prime oscillates?
sorry, can you speak a little louder? I can hardly hear.
Sorry. Okay. From f minus g prime oscillates.
Yes.
Can you not get that f prime minus g double prime oscillates?
Yes.
But they both live in K.
F prime minus G double. F prime, where is F? F was in
K.
F is in K, but then the derivative
in K,
of F.
in the real closure of K. Sorry.
Yeah,
which
right.
Is Hardy
That's
field,
right.
Which is a Hausdorff field, right?
Yeah, F prime is in the real closure of K. That's right. And so let me see. So let me. Okay, so F prime minus G double oscillates, and they lie both in the real closure. And that seems to be impossible.
Unless they are zero, right?
Yeah, okay. This is much easier. Thanks.
But I mean, I don't know, maybe K is not closed. Yeah, no, sorry, because K is not closed under derivations, is it?
No, but oh, right, yeah. I mean, the derivative of,
it was
yeah,
stupid.
okay, now I see the derivative of K it lands into K plus KG prime. And
yes,
that might
right.
not,
sorry.
That might not be in the real closure of K, right? Yeah, okay, so no, I thought for a moment that you had shortened the proof by a lot, but no, I think we have to do a bit more work. H prime, right? Hence, H prime oscillates by an earlier remark. Now, what is H prime? Now, H prime, by the usual arguments, P delta G prime plus P prime G prime G double, right? P delta being obtained from P by replacing each coefficient Pi by its derivative Pi prime. And so, and this can be written as Q G prime, where Q is a, well, Q is a differential, sorry, a polynomial, just a polynomial over K. Using the fact that G double is in K, G double is in K. Right. The coefficients of P lie in, wait a minute, now I'm a little, oh no, yeah. You have to be, the coefficients of P lie in delta K, which is in other words, they are sums of elements in K and then K times something in G prime. And if you express these coefficients that way, and you also use that G double is in K, you will see that H prime is indeed equal to QG prime for Q, a polynomial in K. And if you carefully look at the degree, you will see that the degree is still less than or equal to n, with degree Q less than or equal to n. Well, certainly if you take P prime here, the degree in Y goes down. So that is not a problem. And G double here is in itself in K. Here you have to pay a little bit of attention. If you the point, here you use that P is monic, right? P is this monic polynomial y to the power n. In other words, if you take P delta y, the first term disappears. You end up with P1 prime y to the n minus 1 plus dot 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 Pn prime. And that means that the degree goes down by 1. But then because the pi primes are in capital K plus capital K G prime, degree can go up again. So you end up still with degree at most n, right? So, so let me say using delta K plus K prime, delta play, delta K contained in K plus K prime, and P being monic, P monic. Okay. Now we factor, yeah. Yeah, why is it not 0, by the way? Well, H prime is oscillates, so it's certainly not a 0 function. And so Q cannot be the 0 polynomial. Now Q has a factorization over the real closure of, which is H, a factorization Qy equals little q times y minus phi1 y minus Vm, and then some well, quadratic irreducible, so to say. So let's write it as Q1y, where Q is simply a non-zero element in my field capital K, and the phi1s are in the real closure. And Q1y, a product of the usual kind of factors y plus eta. Anyway, they are not going to interfere with the argument. Theta square, eta, theta, in the real closure, and theta not 0. Yeah. So if we evaluate this at large t, this will always be greater than 0. Right. So for sufficiently large t, we have Qt not 0. And so, and also Q1, Q1 G prime, when I plug in G prime, T will not be 0. And H prime T, right? So H prime was QG prime. Q is factored now, and now we substitute G prime back into little g prime for capital Y here, and we get that H prime T, and also substitute large T, and we get that H prime T equals QG prime T is QT times, G prime T minus V1 T G prime T minus VMT times, well, let me just write it here, Q1 G prime T. And so now H prime was oscillating, and that means since little h prime was oscillating, and since Qt is not 0 for large T and Q1 G prime T is not 0 for large T, that means that for arbitrarily large T, we will have that G prime T equals phi IT for some I. Yeah. So and if let me so G prime T equals phi IT some I 1 and 2 M. Right, but since H prime is oscillating, there will be one I for which this happens for arbitrarily large T. Yeah, so we have a single I in 1 up to M, such that G prime T equals phi IT for arbitrarily large T. So G prime, let me see. So G prime minus phi I oscillates. Or G prime equals phi I. Now, why is, let me see. Why, yeah, that last possibility is actually not possible. Yeah, G prime equals phi I would give G prime since the phi i's are in the real closure, would give G prime in HGRC. But then F would have to be empty, would give H in, sorry, not in KRC, give H in HGRC. So, or in, let me see, what was the definition of F again? F, yeah. So contradicting, but then, then F would have to be empty, right? If you go back to the definition of capital F, if G prime happens to be in this real closure, then of course the difference of G prime with anything in this real closure would not oscillate, and so so this cannot happen. So F is empty, contradiction. Of course, you could also simply say, well, if G prime is in the real closure, then we are really done already. But then you would, okay. Right. So one conclusion we can draw now is that Q prime, sorry, that Q is of degree at least 1. Hence, it cannot be a, well, I guess we could have concluded this earlier, but let me see. Oh, yeah, well, it's rather obvious, right? We have an I in 1 up to m, which means that m has to be at least 1. Otherwise, that in the statement here, m could be 0, but since there must be at least one I between 1 and m, that means that m has to be at least 1. And so q is, of course, of degree at least 1. And phi I will be an f. This phi I that we have fixed here must be an element of f. And so, in other words, f intersected with phi, which I will define in a minute, is not empty. Where capital Phi consists of all the phi i's. No, it's just a phi. Yeah, yes. Where capital Phi is simply all the solutions in the real closure, all the roots, so to say, of the equation q phi is 0. This is simply phi 1 to phi m. Right, so f has at least one element in common. Now, the next thing is that I claim that it's actually just one element that is in this intersection. In other words, phi I is the only one. Phi I here is the only thing in the intersection. Suppose otherwise. Then we have, well, then we have at least two elements. Then we have phi less than xi in f intersected with phi. We have two of those phi i's, and such that g prime minus phi and g prime minus xi both oscillate. Both oscillate. Right, but now from q phi equals q xi is 0 and phi less than xi, we apply roller. Roller applied now to the real closed field K, the real closure of K. Yeah? Roller gives a row in the real closure. Row in the real closure such that phi less than rho less than xi and q rho prime is, wait a minute, yeah, q prime rho, right? Think of q as functions, continuous functions over a real closed field, and with zeros, phi and xi, with phi less than xi, and then you get this. Okay, but the point is that then g prime minus rho must also oscillate, then also rho must be an f. Well, if you draw pictures, you will see why, right? If you draw the graphs of phi and xi and g prime, phi is ultimately below xi, and the graph of g prime will intersect the graph of phi infinitely for arbitrarily large t, and also the graph of xi will intersect for arbitrarily large t. And now the function rho, the graph of that lies between the graph of phi and the graph of xi. So obviously then G prime must also intersect the graph of rho for infinitely large t. Yeah. So okay, now let me see. Yeah, so by drawing the graphs of all these functions in your mind, you will see that this is clear. But of course, that means between any two. Let me see now. Why is that a contradiction now? But Q prime is not 0. So and the degree of Q prime. This is the nub of the matter. The degree of Q prime is less than n. Yeah, the degree of Q was less than or equal to n, but then its derivative with respect to y is less than n, and then you have a contradiction with the minimality that we assumed. Contradicting the minimality of n. If you go back to how we introduced n, let me see. Where did I? Yeah, let little f in capital F be of minimal degree n over k. And here we have a new element, rho, which is of lower degree. Rho satisfying the equation Q prime, rho is 0, which is of lower degree. And so we have a contradiction. And so the claim is proved. Right? Okay, so therefore, from now we are close to the end. From phi intersected with F is phi say. Yeah, any question?
Yes, sorry, Lau. It's about when you say Q of phi equals Q of psi equals 0, it is as germs, or it is there is ultimately infinitely many t's?
No, it as germs. Q phi is an if you Q is this polynomial over k, and everything takes place in this very large ambient ring of germs, of continuous germs. And so Q phi is 0 means, of course, it's the same as saying that Q phi evaluated at all sufficiently large t is 0.
But then identically 0.
Well, for germs,
yeah,
I
ultimately.
mean, as germs, they are 0. They are the 0 germs.
Okay.
Right, and I apply roller to the, we are using here the Starsky theorem that since roller holds for polynomials over the ordinary reals, it holds for polynomials over any real closed fields. And so that's what we are using here. It's not the ordinary roller, in other words, it's the roller for the real closure of H G.
Thank you.
Or K or the real closure of K. Right. From F phi intersected with F is empty, say, we get for arbitrarily large I hope that the term arbitrarily large t is clear. It means that for any t0 there is some bigger t for which it happens, right? It does not mean all sufficiently large t. It means there are arbitrarily large t. we get for arbitrary large t, if h prime t is 0, which will happen indeed for arbitrarily large t, then also g prime t equals phi t. Let me see, where am I? Why am I? Why is this? H prime t, then g prime. Yes, right. H prime t is qt times g prime t minus phi 1t. So phi is one of those phi i's, and so whenever h prime t is 0, yeah. So g prime minus all the other phis will not be 0. So it's only for this particular phi that it will be possible to be 0 for arbitrary large t. Right. We now show that that this is impossible. We now show that p phi, which is an element of the real closure, has impossible properties, contradictory properties. And we will be done. On the one hand, yeah, consider first the case that p phi is positive in this real closure. Then for all sufficiently large t, we have with for where h prime vanishes, and this will indeed and it will happen for arbitrary large t. We have that ht equals pg prime. Yeah, that was h was pg prime t is p phi t. Is bigger than 0. But h, yeah, but of course, but h oscillates. And but this contradicts this earlier, this contradicts this lemma about oscillation in the beginning, contradicting 511. Right, for all sufficiently large t where h prime t is 0, ht will be positive. Right, let's go to 511. Yeah, if you have a C1 germ that oscillates, then there can be arbitrarily large s's where h prime s is 0 and h s is bigger than 0. But in that case, in case 1, there are also arbitrary large s's with where h prime s is 0 and h is not positive. And here we actually get to say that, yeah, here we are contradicting that. Right, for all sufficient large t where h prime t is 0, ht will be positive and not less than or equal to 0. Yeah. Okay, and the case p phi negative leads, yeah, gives a similar contradiction. Simply using case 2 of that lemma gives a similar contradiction. And so does the case PV is 0. I mean, I'll leave you to think think a little bit about this last case. I mean, it's just, I think again you can use this lemma 511, but that's the end. I mean, so this is the main theorem in that paper, and I'm glad we got through it. Let me see what's the time now. Okay, yeah, I almost used up the hour. So now we can start. So we'll get to use this. Again, this raises the issue, the question. Well, no, let me not. Yeah, let me just make one remark. It would be interesting, I think, to also have a generalization of this theorem to the R tilde Hardy field setting, right? So then H would have to be an R tilde Hardy field, which is a model of T. And you have a germ little g, which generates a R tilde domain over H, such that G double is in the T closure of that. And then it would be interesting to show that G generates an R tilde Hardy field again over H. My guess is that, of course, you would need some kind of replacement for this lemma then too, right? This uses polynomial algebra, and you have to replace this, or minimum polynomials, and you would have to replace this by a somewhat different argument. But otherwise, I think, well, and here, of course, the proof by induction, or not induction, but by taking a minimal degree, also seems to use very much things about polynomials. But nevertheless, I have the feeling that they should generalize to the R tilde Hardy field setting. So if someone would like to do that, I'd be interested to hear. Anyway, let's go to 5.2, and here I simply want to review basic facts about linear differential equations. Review things on linear ODEs. I mean, this is standard material that you can find in any reasonable book on differential equations, but I think it would be good to review that and also introduce notation that we are going to use. Yeah, so it will be useful to have a slightly more general notion of R times continuously differentiable function, where the domain can be any set of, instead of just an open interval or an open set, for any set I and R, a natural number, or infinity or omega, we set, and I'm just taking an easy way out. I say the R times continuously differentiable functions, or the real analytic functions, if R is omega, is simply those that extend to some R R times continuously differentiable function on an open neighborhood of I, right? So it's the f from I to R, where f extends to a function in CRU for some open, and of course for open sets, we know what that means for some open U in R. And of course it should contain I for some open containing I. Otherwise, extending wouldn't make any sense. So it's just the restrictions of the R times continuously differentiable function on open neighborhoods of I. Okay, now let me fix R to be a natural number. So I drop the cases where R is infinity or omega. And let's just consider now an interval, but it can have endpoints in it. Be an interval possibly with endpoints included. So it's not necessarily an open interval, but it must have at least two. It has to have more than one point. It's an infinite. In other words, an infinite connected subset of R, if you like, possibly with. So it's not a degenerate interval like a point or the empty set, with more than one point. So note. Oh, by the way, note also that C0I. I could have done that also already here, there, above, but this is just the continuous functions on I. Yeah? Is f from I to R, f continuous, because a continuous function certainly extends to, on an interval, certainly extends at an endpoint of the interval beyond it. So right. Let F1 Ci. So we have now continuous real valued functions on I, and then we can consider the corresponding linear differential equation. But I'll introduce it as a map. We have R linear map. Let me call it A. From C, this goes from R times continuously differentiable functions I to just a continuous function of I. And AY, how is it defined? It's the R derivative plus F1 times R minus 1 derivative plus the last term is FR times Y, the zero derivative. Right, so this is a linear differential operator, if you like. This doesn't look very nice. Let me. Right, but it's important that this is linear, an R linear map. And the kernel, of course, consists just of the solutions of the corresponding homogeneous linear differential equation, whose kernel consists of the solutions in CRI of the homogeneous. This is just terminology that people often use. The homogeneous art order. The order here refers to the R, the highest derivative that shows up. Art order linear ODE. Ordinary differential equation, which is often then written as an equation. Y is 0. Right. Okay, now actually this kernel has exactly dimension R, and that will be important. So, and I'm going to state this in a somewhat and the next statement will also consider the inhomogeneous corresponding inhomogeneous linear differential equation. So let's call this this is known as the existence and uniqueness of solutions with given initial conditions. Initial conditions. Now, yeah, the nice thing about linear differential equations is that you really have this over the whole interval. In general, for algebraic, for more general art order differential equation, let's say YR equals some polynomial in y prime up to YR minus 1, you have locally at each point with given initial conditions, you have solutions, but they might not extend to the whole interval I. But for linear ones, that is always possible, and so that is very important fact. So now I'm going to fix some continuous function on I, and also some initial point in the interval, some where the initial conditions will be given, and see initial values will be given by numbers C0 up to CR minus 1. Right, then there is a unique solution, which while Y, which unique. So I'm going to indicate here the dependence on the data G. Wait a minute now. Am I? Yeah. Yes. The data are the given function G, then T0, and then C, this tuple of numbers, such that the initial conditions are satisfied. So the value of Y at T0 is C0. Sorry, C0. The value of the R minus 1 derivative. We can arbitrarily prescribe the values of these derivatives at the initial point t0, and y satisfies the differential equation. Well, ay is g. Yeah. Yeah. Remember, ay is this linear operator, or this linear. Right. So that is the okay. And if you now apply this to the case where g is the zero function, you get exactly, yeah, for g is 0. This yields an R linear. Isomorphism or bijection. Isomorphism. C goes to y 0 t0 c from well, this goes from RR to the kernel of our operator. The kernel in where we consider, of course, R times continuously differentiable functions for which this makes sense, right? For this differential equation ay equals g to make sense, you have to assume that y is R times continuously differentiable. Well, you might say, why don't you just assume it's R times differentiable? But once it's R times differentiable, it will be continuously differentiable R times as well, because yr is equal to minus f1 yr minus 1, etc. So that really no restriction. Okay. So that means, in particular, what I already said, that this kernel is finite dimensional as a vector space over R. Its dimension is exactly R. Okay. Yeah, and of course, for an arbitrary G, the solution set is just any particular solution plus the kernel. Yeah, for arbitrary G and any particular solution.
Excuse me, Lau. Don't you need class C1 for the coefficients Fi or Lipschitz or something like that in order to have uniqueness? I am confused.
I don't. Well, I don't think so. You see, when you translate this into a system where instead of y prime, yr, you simply introduce new variables, then you get a system of linear in matrix form, so to say. And there, the Lipschitz condition that you want to have is actually satisfied.
Oh.
Let me check this again, but I'm pretty
okay.
sure.
Yeah. Oh, okay.
I'm pretty sure
I,
that
I think yeah. So. Yeah. Sorry.
Okay. Yeah. No, I think this is really correct as stated. And in particular, y0 in CRI with a y0 equals g, we have the entire set of solutions is simply a translate of this I0 by all the elements in the kernel. I mean, this is just, of course, just trivial linear algebra using the above statements. Equals y0 plus the kernel. Because any solution of the corresponding homogeneous way, right? Okay, so this is just saying just iterating a well-known fact, but yeah, we also want to say something about the Wronskian 522 criterion. Yeah, in practice, it is actually important to have a basis for this linear, for this vector space over R of the homogeneous equation. Yeah, and so it's a criterion for why one to YR in CRI to be a basis of this kernel. CRI. Let's. Yeah, so this is this story about the Wronskian. That Y1 R the Wronskian, that Wronskian, this determinant, the Wronskian is, well, let me just write a W here, but if I write the Wronskian, if I want to show how it depends on Y1 and to YR, I'll write it this way. But it's the determinant of this matrix Y1. So the first row, Y, and then the next row you take the derivatives, and the rth row you take the R minus 1, sorry, 1 derivatives. And if you look at, I mean, this is a priori just some element in, yeah, you do this, all these things are actually in C1, all the functions indicated here in this matrix are C1 functions, right? Because you take only R minus 1 derivative is the highest derivative that you take. So this is an element of C1I. So it's right. And now one thing that is rather easy to check, yeah, easy. If this Wronskian is not 0 for a single t, for some t, then they are linearly independent over R, are linearly independent, right? Because if you had a linear combination C1Y1 plus C1 plus CR YR is 0 with coefficient C1 up to CR in the reals, not all 0, then the same linear combination also holds for the derivatives, and so you get actually that that you get a linear combination of the columns will be in this matrix will be 0. And so and then the determinant would always have to be 0. Right. Now, but what is important for us is the case where Y1 and 2YR are in the kernel. Yeah, that now. Kernel. This operator. Then, well, let me make two statements. Yeah. if Wt is not 0 for some t, it will be actually not 0 for every t, which we can also express by saying that it's a unit in this ring of 1 times continuously differentiable functions, right? So Wt is not 0 for some t, then it will be non-zero for every t, and therefore a unit in this ring. And this is equivalent to y1, yr is a basis of this kernel of the R linear of the vector space kernel. Oh. Yeah, again, let me mention another fact which is interesting and useful. This W, as I mentioned, is still a continuously differentiable function, so you can still take its derivative, and it actually satisfies the following differential equation, which is now of order 1. In fact, it follows that what is it? No, it's Wt0 times integral of, no, it's the, sorry, I got it wrong. Next, of this integral. Well, that holds for any function that satisfies a differential equation like that. You can always x minus integral f1 s ds on I. On all of I, you have, okay. Let me see, what is the time? Yeah, okay. I also want to say that all the above goes through in the complexified setting, right? So yeah, let me all this, and that's important as well for us. All this goes through right, for R. Again, here we can allow also infinity omega CRI. So now I'm working, right, so we by adjoining I, basically what we are considering are functions on I that are complex valued, and so the function has a real part, which is then an element of CRI, and a complex and a purely imaginary part, which is also in CRI. And the usual derivation, yeah, and the usual or the standard derivation that we have on C1, f prime from C1i to Ci, they take just extends to, that's also called standard. derivation. Yeah, and of course this derivation map C for r greater than or equal to 1, it maps CRI to CR minus 1i. Extend to the standard derivation f plus gi goes to f plus gi prime, which we simply define, well, if you like, this way, from CRI to CR, or C1, sorry, CI. Yeah, FG. Right. Okay, good. Yeah, and now we can consider these differential operators with coefficients, not just real coefficients, but complex coefficients. So let R be a natural number, and let now F1 FR in CI I. So they are continuous functions on I, but complex valued now. And then we have the instead of R linear, we have now the C linear map. A from C R I to C I, and AI is now, as before, plus I. Okay, and now I just want to say that the existence and uniqueness goes through. Now existence uniqueness goes through the statement. Of course, the interval I is remains the interval I, but with but the role of the real scalars are and CI, CRI replaced by C, CII. Right, so if you just go through the statement again, you will see that yeah, so G will now be a complex continuous function on I, and now C is an R tuple of complex numbers, and then there is a unique Y. Oh, I never thought to say that, I forgot to say that Y is in CRI here. Yeah. And of course, in the complex situation, CRI with little I adjoint. Right. Yeah, so then here you have, instead of R linear, you have C linear, and you have C to the R here, and here you have CRI with little I adjoint, and so on. I think it makes, it will be clear. And also the whole business about Wronskian goes through. Yeah, so also, let me see, also the definitions facts about Wronskians. For go through for, but now of course we are considering functions y1 and 2i r and c r I, little I adjoins. Okay, and I want to just look at one example. Although that's again, let's say example y double plus y equals h, and here h is in ci, and of course here the operator and what is the kernel? Well, you all know that the kernel contains the sine function and the cosine function, and they are linearly independent, so they already must form a basis. Yeah, and the kernel C2i yeah, let me write it clearer. Kernel C2i a is r sine x plus r cosine. The linear combination of sine function and the cosine function. Here x is simply the identity function on I. Right, and right. Yeah, you can actually easily check that the Wronskian here is just one node. Yeah, node. If you compute the Wronskian of sine x, cosine x, well, okay, sine x, cosine x, sorry, it's the determinant. So let me put a straight, and then cosine x minus sine x. And if you compute it, you get 1, right? Which of course is in accordance with this differential equation that the Wronskian satisfies, because in this case f1 will be 0, and it says w prime is 0, which is true. Okay. I'm close to the end. Well, I still have, let me see, where is the time? Oh yeah, I still have
12 minutes, something like that.
Yeah, okay, let me make a few more remarks. Yeah, as to solving y double plus y equals h, I want to, yeah, once you have a basis for the homogeneous, for the vector space of solutions of the homogeneous equation, you can actually come up with formulas for solving also the inhomogeneous equation. I'm not going to write down this in general, but let me just do it for this case. For as to solving y double plus y is h, where h where h is as above, we always have the solution. We have the solution f in C2i given by, well, I simply write down explicitly the solution, namely you start at some arbitrary point t0 in I, and you integrate up to t sine t minus s. So s is the integration variable, hs ds. Right, so this looks a little bit magical, perhaps. This is the solution to this differential equation. It's not even obvious from the way this is written that this is a C2 function, right? H is only continuous. H is only continuous. The sine function here, of course, is C infinity. So you might think, okay, it's C1 because its derivative is well, anyway. But it actually turns out to be a C2 function. And let me say, let me leave this as an exercise to see this. Recall, yeah, it is better to write sine t minus s as a linear combination of sine t and sine s and cosine t and cosine s. So, not, sorry, as an expression as the following. Recall that the sine of alpha plus or minus beta equals sine alpha cosine beta plus or minus cosine alpha cosine beta. Well, this is for alpha beta in the reals, but of course also in the complex numbers. I mean, but we need it here only for the reals. And this allows you, so by writing sine t minus s this way, and you can then explicitly differentiate f, and then the result you can differentiate again, and you will check that it solves this equation, yeah, which allows explicit differentiation twice. And then you can just plug it in for once you have computed the second derivatives, and you will see that you'll end up with h. Okay, so this is actually something that we will heavily use next time. And now it's yeah, let me just say that the next section will be subsection will be solutions of y double plus y in Hardy fields. Is H in Hardy fields. Right, but that will be next time. So, but there is. Shall I stop here?
It's up to you. Do you want me to stop the recording?
Well, let me see. Yeah, let's stop here. But of course, if there are any questions, I can answer them now. But there is also this question session afterwards, right?
Yes,
Which starts when?
it's up to us. I mean, it can start at 11 or at 10 past 11. It's up to you to say when.
Okay, let's start it at 11 then.
Okay.
Yeah.
Okay.
So
thank you. I stopped the recording then.
yeah. Okay.